Right, now we are coming to the fourth part, and we are about in this course on modeling and simulations of machine component systems. And I will continue to discuss lumped models, and in this case I will talk about hydraulic models. So that's models you may meet in if you want to model a hydraulic system, for example, or if you want to model a system where you have fluid components in some way. Normally it's a hydraulic system, but it can be other systems too. And again we will talk about these resistive, inertial and capacitive types of relationships. And now we are talking the effort is always pressure and the flow is always fluid flow. So we starting with the simplest is the fluid resistance. So if you have a long pipe or hose channel or something, you have fluid coming in one end at a certain pressure, it comes out in another end with another pressure. And in the resistive model, the relationship is just there is a pressure drop because there is a resistance of flow through the pipe or hose, especially if it's very thin or small diameter. And so the difference between the pressure out and in is simply a resistance, a constant multiplied by the flow. And this for a laminar flow, straight pipe, this resistance coefficient can be determined as 128 multiplied by the viscosity multiplied by the length of the hose, divided pi and divided by the diameter with a power 4. So here you can see that the diameter is extremely important. So if you make it 2 times bigger, the resistance will decrease by 16 times. So diameter is very much the most important parameter in this case. The inertia then, well, the inertia comes from what we have learned here, it's from the time derivative of the flow effort. So if you suddenly change the flow, there will be a change of pressure in the inlet and the outlet ends of the pipe. So if you suddenly increase, for example, there will be a bigger difference. If you suddenly decrease, there will be a small difference between the pressures in and out. And this proportionality constant is the fluid inertia, and that is determined as density multiplied by the length divided by the area of the pipe, so the cross-section area of the pipe. That could also be very useful. And the third one, the capacitive type of relationship, is coming from something called fluid stiffness or maybe also wall stiffness of the system. But let's stick to the fluid stiffness. Even if we normally use oil in hydraulic systems, and oil is pretty much it's very difficult to compress, but it's not completely incompressible. So at high pressures it will be deformed and it will be compressed a little bit. So, and if you have big volumes, then this deformation may have an influence. And as I also said in the beginning, the walls may also be deformed, and you may include this into the fluid stiffness also. But again, it's a parameter coming from the continuity equation like this. If you see your system as a system where flow is coming in here and flow is coming out here, and you have a certain volume. So the difference between the flows in and out is what is stored in here in this volume. If in a steady state, under steady state conditions, the QI and the QO must be equal, otherwise it something will be stored all the time here, but during short periods, during transient changes of something, you may have some storage in here, and this storage is written like this. It's actually it's a bad way of writing it here. I will come back later, but it's a change of the volume and it's a change of the pressure, and we normally call this a pressure, a capacitance, this parameter. I'm coming back to this. I think it's better to show it via some mathematics, but it's very much about the capacitance of the oil here. It's the volume divided by the bulk modulus. The beta is the bulk modulus, and that tells you about how compressible the fluid is. So coming back to that. So a more general way to describe this is to make a fluid volume element, which is it's a lumped model element with the Q in and the flow in, pressure in, and Q out, flow out, and pressure out. Could also be, in some cases, you may need to use the mass flow instead of the volume flow, but and then you need to introduce the densities also. But for this element, we apply the. You remember when we discussed to make a model, we must identify equations, and the equations are identified by searching for the laws of nature. And in mechanics, and especially in fluid mechanics, these two are very typical to apply, of course. It's a flow continuity and a force equilibrium. So, if we start with continuity then, now coming back to that, I had some problems to describe earlier. We see on the mass flow now. So the mass flow in is the density multiplied by the volume flow in minus density and flow out, and that the flow that is stored inside the volume is then the time derivative of the density of the volume. Try to understand. Stop the video and try to see if you understand that. It's of course the change in time of the volume. That's also flow, and the difference between input and output is this change of volume, or mass actually in this case. And if you don't have any change of volume and mass, this term is just zero, and these terms are equal. That's a steady state conditions, stationary conditions, where the flow in is equal to flow out. Okay, but let's take the more general case where you have a change. If we expand the right hand side now, you obtain a dV dt, and you get a term. You get also a term d rho dt. And look here now that I assume that the density is about the same in both inlet and outlet, and of that reason I can just move the density term down here, so the density vanish from this term and it comes here instead. So this is the expanded and simplified continuity equation. And then I also introduced the equation of state. That equation of state tells you the relationship between the density and the pressure. And for these cases we use the bulk modulus model. That means that the derivative of density with respect to pressure is simply a proportionality constant 1 over beta multiplied by the density. And this proportionality constant is called the bulk modulus, and for a typical oil, it's something like 1500 megapascals at room temperature, and atmospheric pressure. It increases for increasing pressure, decreases with increasing temperature. Okay. Then we make use of this equation and put it into this equation. Then we end up with something like this. So we have the fluid flow difference minus the volume change is equals to a capacitance, a constant multiplied by the change in pressure. Where this C, I called it capacitance already, it's the volume divided by the bulk modules. The bigger the volume, the softer the lubricant, the bigger the capacitance is, the more okay. Or we can also rearrange it a little bit to show that it's the P, the relationship between the P and the Q in that way. Okay, so that's one part of this story. Yeah, that was when we applied the fluid flow continuity equation. Okay, now let's make use of the other law. That's the force equilibrium. So if we apply the Newton's second law, the pressure, the force in the different ends of this fluid flow element is simply the pressure multiplied by the area in the inlet minus the pressure and area in the outlet minus the resistance forces should be the same as the mass multiplied by the acceleration of the fluid. So now if we assume that we have a pipe, we assume that we have a laminar flow. You better read some fluid dynamics basic books. If you have a problem to follow this, you should read some fluid mechanics book. So putting things in here and deleting the areas or moving the areas to the other end, then we get that the pressure in minus the pressure out is minus the resistance multiplied by the Q, which is a delta P in itself, is something called the mass of the element divided by the area multiplied by the QDT. Well, maybe a bad explanation here, but if you want to change these to something we already know, we know the diameter of the pipe, we know the density of the fluid, we know the length of the pipe, and then you can rearrange this to something that looks like this, and you then also can identify this as an inertia coefficient or inertia constant. So you end up with something like Pi minus Po is the resistance multiplied by the flow plus the inertia multiplied by the time derivative of the flow, where the R and the L is according to this relationship. Okay, so if we summarize the fluid pipe element, then it's that we get from the force equilibrium we get this equation, and from the continuity equation we get this one, and you may also make use the flows here are pretty much the same. So in what Q to apply, should we apply the inlet Q or the outlet Q? So in this equation, so I suggest that you simply use the average Q. That gives you a good measure of the Q. And if you may also need to know the pressure. Should we use the pressure here or pressure there? You can use the average pressure if you need that too. So that's the fluid element. Some typical machine components we're going to face probably in our life is the hydraulic cylinder, and hydraulic cylinder, then it's a very straightforward relationship between the force and pressure, and the flow and speed. So if we if we fill this chamber with flow, and this is, then it will move with the Q multiplied by, sorry, it will, it depends on the area here and the flow that will give you the speed will be Q over A then. Maybe easy to understand. And the pressure is of course the pressure multiplied, the force is of course the pressure multiplied by the area here. So that's a very simple model where actually there is no connection between the flows and efforts there. The flows are connected and the efforts are connected. But fluid inertia, resistance and capacitance may also play a role. For example, if we must move this quickly, and resistance may play a role when it leaves and entering, maybe some holes here that stops the flow a little bit. And if this is a very big cylinder, the fluid volume may also play a role. So if you a little bit more complex model for the cylinder can be found on this slide. So again, we make use of the of the force equilibrium. So in this case, the mass is the mass of the piston, and maybe something connected to the piston. So it's the forces on the inlet side, forces on the outlet side, minus the applied force here. While the flow, the force equilibrium forces, or the fluid element equations now can be used here. So the relationship between the pressure here from the system into the inlet chamber is given by this relationship. So, and the Ri and the Li here is the resistance and inertia of the system before entering the cylinder. And also the continuity equation can be applied here. So the change of volume is the change of, it's depends on the x dot, the speed here, and the areas. Please see here now that the area here is bigger than the area here because the rod is changing the area slightly. And that is then you have the dp dt, and there is one dp dt here, and it's one dp dt here, and so there is one capacitance here and one capacitance here, which is increasing as this is moving this direction. It increases, and that one is then decreases. So this is the C for the inlet and C for the outlet. So you can simply apply these equations if you want to make a more complex model of your hydraulic cylinder, if you have a sudden motion of it, for example. Now, that was. And another component that you may have in your system is an accumulator. So sometimes you add some extra volume in the system to store, to avoid pressure ripple or pressure variations in the system. You may add a volume like this with a gas bubble here, where you keep a bubble where you have a certain gas pressure with. It's preloaded by the gas pressure, and so you may say that the pressure inside here is constant. And then you can find the relationship between the flow into the accumulator and out into the outlet, and this relationship looks like that. It can be also useful from time to time. And note here that the N is the polytropic index, and we may assume that it's 1.4 here. So, to summarize the hydraulic relationships, resistance is just simply P. The direct proportionality constants is the resistance between the pressure and the flow, and the inertia, then it's the between the pressure and the flow, a time derivative, and capacitive or stiffness is the pressure and the integral of the flow. Or more typical, we see it as the flow as a time integral, time derivative versus the time integral. So, and I should also say a few words about electrical relationships. It's the same thing here, resistance, that's the electric resistance. We don't call it inertia when we talk about electric relationship, you may remember. We talk about inductance. So the L is inductance, but it follows the same pattern. But we call it capacitance when we talk about the flow integral. So that was all about lump modeling, and when you are going to do some programming here and using Simulink, for example, then I suggest that you do according to the following. You write down all the equations. You may rewrite them to integral form because then you can make use of the Simulink's 1/s box. And remember the initial conditions. You may remember that I missed that in the part 2, where I made my Simulink program. So when you integrate, you really remember that you must take the initial condition into account. Otherwise, you get wrong absolute values. And then you start programming graphically. You take each equation and you connect them to a plus or minus block, the sum block. Use the gain blocks, product blocks. There is also there are many possibilities in Simulink, and I showed you the very simplest way of using it. And if you have a bigger system, you may form subsystem, and you may make ready-made. If you have a hydraulic cylinder, for example, you may make ready-made blocks for a hydraulic cylinder, and then you don't need to make it a new one all the time. Or if you have some standard components, you may store them as subsystem blocks. So then you can use the same component many times. So that's something you can learn later, and this is all for now, and I wish you good luck with the modeling. Bye bye.